This lecture will cover the laboratory math for urinalysis. Now we did briefly touch on urinalysis and what all was involved in the urinalysis department within the laboratory in our intro class. But I just kind of want to reiterate that urinalysis is one of the most important or most common tests that is performed in the laboratory, and that they do this by using strips that have little test pads on it that have been impregnated with some sort of chemical that, once it comes in contact with the urine, will form some sort of chemical reaction that is measured through the color change that happens in that pad. Also, additionally, outside of the chemical analysis of urine, there's also the macroscopic and the microscopic analysis. And with the microscopic, you're looking for those cellular elements. And of course, urinalysis can be used as a good screening tool for different diseases, conditions, things like diabetes, urinary tract infections, different metabolic disorders, liver disorders. So with urine being one of the easiest samples to collect, it does make it a very vital and important test within the laboratory. Now, one of the parts of doing testing on urine is to check for the specific gravity of the urine. And so the specific gravity is basically looking for the quantity of dissolved solids that are within that urine. And so this could be things like urea, chloride. Years ago, the specific gravity was done by the use of a refractometer. And so what the refractometer does is it measures the total solids per meter. And so this little device almost looks like a little telescope type device, really small handheld little device that you would place the drop of urine on and look for that line in that urine that is kind of showing you that refractive index of that urine, which is specifically or indirectly related to that specific gravity. Now, that refractive index is basically a ratio of the velocity of light in the air to the velocity of light in the solution. So what it's doing is when you hold that up, it's kind of comparing that reflective angle of that light as it passes through that urine solution. And then there's kind of some mathematical conversions that will translate that out to this actual specific gravity. So not a lot of labs actually use the refractometers anymore. Even some of your student labs, a lot of student labs don't have a refractometer. The only place you might run into using a refractometer would be any lab that's more specialized for urology type clinics, any kind of dialysis, anything like that. They may have a refractometer in their lab, but you may not ever encounter the use of a refractometer, but there are still places that use them. Refractometers are used some in like distillery type things, like making beer or different things like that, ales. However, in the laboratory, using it for urinalysis, you do have to calibrate the refractometer. So you would do that by placing a drop of deionized water onto it instead of your urine sample, and you're looking for it to read at 1.00, or you could do a 5% weight per volume solution of sodium chloride, and that is supposed to read at 1.022. Now, if you were to actually have a refractometer and you do the calibration process, and let's just say you have a scenario where you put let's just say the deionized water. Let me get my writing tool here. And you put the deionized water on there looking to do your calibration and for it to read at 1.00, but instead it reads at 1.002. Well, because it's reading 0.2 over that value, that calibration value, then any sample that you read after that, you're going to have to account for that difference there. So you would need to actually subtract that 0.002 from every sample value that you got from then on. And so that's part of your quality control process for that particular sample based off that calibration. protein and glucose are both higher molecular weight compounds. So with that, what happens with these higher molecular weight compounds, they actually will start to increase the density of the urine. With protein, it will increase it by 0.003, and then with glucose, it will increase it by 0.004, and this is for every 1 gram of protein or of glucose. So what you need to do is, if you have protein or glucose values that are greater than 1.0 grams per deciliter present inside of that urine, then you will need to account for that by doing corrections of that specific gravity. So with protein, what protein does is it's not normally found within the urine because those protein molecules cannot actually pass through that glomerular membrane. So when you start seeing the protein spill over, then that means that something with the integrity of that glomerulus has been compromised, and this is usually due to some kind of injury or disease, which allows those proteins to start passing through and being excreted within the urine. So with doing that specific gravity, you're able to kind of assess the concentrating ability of the kidneys, and which is primarily takes place within those tubules. So when you start seeing large amounts of protein, then you know that there's some issues going on with those glomerulus, but you need to account for that excess protein for that specific gravity value there. So to do that, you would need to subtract the 0.003 for each 1 gram that is present of protein in that urine, and then you would do the same as well for the glucose. So here we're going to look at an example. So if we were to do a correction for protein, our urinalysis of our sample revealed that we have 3 grams per deciliter of protein, and if we were to have read it on the refractometer and we got a specific gravity of 1.026, then we need to correct for that because our protein concentration is over 1 gram per deciliter. So because we have 3, we will need to take that 0.003, multiply that by 3, so that gives you your value of 0.009, and then from there you would subtract that from your refractometer value of 1.026, which gives you a 1.017. So your corrected value for that specific gravity of that particular sample would reflect the concentrating ability of the kidneys at a 1.017. Now the details of what all of this means, these values, we'll talk a little bit more when we actually get into the urinalysis course. And here we have an example for glucose. So our urine specimen revealed that we got 2 grams per deciliter, so that is above the 1 gram, with a specific gravity read from the refractometer of 1.018. So we need to account for those 2 grams. Multiply that on the 0.004, gives us the 0.008, and then when you subtract that, then you get your value of 1.010 for the corrected specific gravity of the sample. Now urinalysis can kind of branch over into your chemistry department because sometimes you're looking to determine how the kidneys are functioning, how good of a job are they doing, are they starting to decline in their function. So some of the things that we can do is kind of get a quantitative analysis of different chemical components that are within that urine. And so this can be done in chemistry. So a lot of your chemistry analyzers will test your blood sample. So it can test whole blood, serum, plasma, depending on the particular test, but they can also test things like urine, and sometimes other body fluids, just depending on what the analyzer is and how the manufacturer has designed that analyzer. But you can see it kind of branch over to urinalysis. And so with looking at a chemical analysis, we're usually trying to get a quantitative value, so an actual number value. And what we're looking for is trying to figure out a particular analyte and how much of that analyte is in that concentration of urine. Now, this urine could be collected over a specific amount of time. It can the patient can put out a particular volume. So one patient may put out more volume over a specific time versus another patient. So there's a lot of calculations that can come into this based off of the volume, the amount of time, the patient themselves, their weight, things like that, that can affect those results, as well as how much of that particular analyte is within that sample. And so what we do is clearance test is most commonly what they're referred to. And what it's going to do is kind of assess all of these components together, and it's going to provide information on the glomerular and tubular function of the kidneys. And of course, the main function of the kidneys is to excrete waste products while reabsorbing water, dissolve chemicals from the ultrafiltrate, and it's also going to determine the glomerular filtration rate. So this whole test, doing this clearance test, is kind of going to give you an overview of how the kidneys are doing its job. So when we're trying to assess the actual function of the kidneys, we're kind of pretty much looking at that glomerular filtration rate. So that's basically the rate at which some sort of chemical is filtered out or cleared from the kidneys. And so we do that by doing the various clearance tests. Now, when we look at the glomerular filtration rate, we are assessing at minimum 3 things. We're looking at the concentration of that particular analyte in the blood, we're looking at the concentration of it in the urine, and we're looking at the time interval for the collection of that urine. So the volume of that urine over that particular time gets factored in here as well. And of course, that's going to give you your overall filtration rate of the kidneys and how they're doing their job. Now, there are a couple of different tests that we can do as far as clearance tests to determine that. So we could do an extrinsic clearance test. So this would be something kind of external. We're introducing something that we're going to measure, something foreign to the body, into the patient, and then we're going to measure the clearance of that particular chemical. So this could be something like inulin or p-aminohypurate. And what you do is these chemicals are actually given to the patient through some sort of IV or something. And then you're actually going to measure the plasma for that particular analyte, for that chemical. And you're going to measure the urine, and you're going to plug those into the calculations. Now, an intrinsic clearance test means you're actually looking for a measurement of something that's actually internal to the body. It's inside the body. So this would be chemicals that your body just naturally processes and breaks down from things that you eat, things that you drink, and just the different metabolic processes of the body. So this would be something like creatinine or urea. And so with either of these tests, however it is, it does go into further calculations and measurements. Creatinine is a waste product of muscle metabolism, and so it is produced at a constant rate, and it's also proportional to the actual muscle mass. Now, very little creatinine is actually secreted by the tubular cells, so the concentration of creatinine in the urine is actually a good way for you to assess the tubular function or the tubular excretion function, as well as the GFR. Now, keep in mind when we talk about measuring the creatinine or the urea, this of course isn't an intrinsic test. And what you can actually do is you could collect the urine over a specific period of time. It could be something like 6 hours, 12 hours, 24 hours, although most places are going to do a 24-hour urine collection in order to do this testing. And then what you're going to do is measure the concentration of the urea and creatinine to determine these calculations. With 24-hour urines, they will send the patient home with a jug, and the patient will have specific instructions of what they need to do for that collection period. So it's usually when you first wake up in the morning. I've seen it done both ways. I've seen it say collect the first morning urine, and then I've also seen instructions that say discard the first morning urine and then collect everything after that. So once you discard the first morning urine, then your 24-hour period starts. So it could mean to keep that first morning sample into that collection container, or to collect the next morning's urine sample, first morning urine sample, in that collection container if it's still within that 24-hour period. So a lot of the places, different places, like I said, I've seen it both ways. So it's going to kind of be, that collection period is going to kind of be unique to the facility. Now, the calculations that are used for that particular creatinine clearance test is going to be this calculation you see here, which is the urine concentration. So once you've run, let's just say it's a 24-hour urine sample, you've got that whole entire urine container there, and you're going to mix it up and kind of swirl it around, mix it up, pour off your sample, and then you're going to test your sample to figure out what the concentration is in the actual urine. And you're also, before you pour it off, you're going to collect the total volume of that urine, and you're going to calculate your volume in mLs per minute. And then you're also going to have your plasma concentration from the blood sample that was collected. So let's do an example of a 24-hour urine collection for creatinine clearance. So a total volume of that urine over that 24 hours. So of course that urine was collected in some sort of urine jug. If you work in healthcare, then you've probably seen these jugs. A lot of them are weird orange color, but I have seen other colors before. But they're usually kind of shaped a little weird. Just a big jug that you'll collect the urine sample in over a 24-hour period. And usually you have to store it in your refrigerator at home. So get some creative ways that these urines will come in different bags and things like that. However, for a total volume of 1,500 mLs over a 24-hour period, of course you would have to figure out how much is that in mLs per minute. So we've got to get it down to the minute. So in order to do that, we kind of have to do a little bit of a calculation. So for 24 hours, 24-hour day, you got 144 minutes. And a 24-hour day, there's those calculations there. So you take your total volume divided by the minutes in a day, which gives you 1.04 mLs per minute. So that 1.04 mLs per minute plugs into your formula. Remember the formula we had, UV over P. And so we got 180 milligrams, which is our urine concentration. So that's how much of the creatinine we've got in that urine concentration when we pulled off that sample and tested, with a 1.04 mLs per minute. So that was our calculation that we got from our total volume here. And then our P is our plasma concentration of 1.44 milligrams per deciliter. And so when you plug all those values in, you end up getting 134 mLs per minute once you work out that equation. So that's your creatinine clearance for that 24-hour period on that patient. Now there are situations where the patient's body mass can actually affect the calculations of those results. So for example, someone that is obese would have a different clearance rate than someone that is really small. So let's just say, for example, a child. So when that happens, when you have someone that is larger than average or smaller than average, then you would need to do some additional calculations to kind of compensate for the fact that that their clearance is going to be a little bit different, simply because their body weight is a little bit different than the average person. So when we look into doing something like that, we kind of got to throw in those factors. Then you kind of got to adjust for the fact that the patient is a little bit larger or smaller. So that's where we would use the patient's weight and the height to use a nomogram to figure out the patient's body surface area and plug that into the equation. So the first part of it, of course, we would keep with that same system of measurement and doing those calculations of plugging all of those values into the equation. So first we figured out how many mLs per minute. So we go ahead and got that. So we're at 0.45 mLs per minute. So what we'll need to do next is plug in for the corrected creatinine clearance. So that's demonstrated here in this equation of CCC, corrected creatinine clearance. So we use our original equation. So we plug everything in there. 120 milligrams per deciliter was our urine concentration. Our volume, 0.45 mLs per minute, which we calculated. And then, of course, our plasma concentration. So you'll plug those values in, and then your standards, when you're looking at that body mass, when you're trying to determine that surface area, body surface area, the standard is 1.73. However, if you use the little nomogram that's in the book, so you've actually got a couple little weird little diagrams or measurement tools type things in the book. So you've got the first one is for your height, the middle one actually is considered your surface area, and then your last one has to do with the patient's the weight. So you got your height, surface area, and weight. So what you'll do is actually find the patient's height on the little chart, and then you'll also find their weight. So if you looked at this example in the book and you looked at that chart, the height and the weight, and then just take a ruler or a piece of paper and you lay it over it, and of course wherever it intersects on that line is your value. So this value was determined to be 2.30. It's a little hard because these hard to read because these the way they are kind of positioned in the book, and of course if you have an electronic copy it's going to be even harder. However, this one was calculated to be 2.30. So once you finish kind of plugging all of that in and work out the equation, so if we originally were to do it without the correction, it would be 8.31 mLs per liter. But because of the patient's weight, we do those corrections, and that gives us 6.25 mLs per minute. The corrected clearance value is lower than the uncorrected value because that increased body size of that patient. Once we figure that in, it gives us that corrected count. So the guidelines for the GFR test, or the estimated GFR test, was changed back in 2002 by the Kidney Disease Outcome Quality Initiative. And so what they established was that basically anytime you run a serum creatinine, then this calculation needs to be done, which kind of will give the physicians a heads up if they need to kind of start watching this patient and watching their kidneys and their output of things. So they might want to start monitoring this patient a little bit closer if they start seeing this GFR migrate towards a direction that causes concern for that patient's kidney health. And so there are three equations that can be used. The MDRD, or the modification of diet and renal disease, is an option, but it is a very tedious equation to plug all of that stuff in, so it's not used a lot. And then there's also the modified MDRD, which is used in a lot of like hospital settings where they're able to program these equations into the LIS, or the Laboratory Information System, their computer system, where it's able to pull these different demographics from the patient's chart and do these calculations for you. Once it's put, those serum creatinine results are put in the computer, then it will generate that. And then there's also the Cockcroft-Gault equation. And so with this equation, it does utilize the patient's age and weight and whether or not they're female. And so once you plug all those in, it gives you kind of a little bit more of a simplified version of it. One thing that we do keep in mind is with African American patients, we do add the addition of the multiplying it by the 1.210 for that value to account for the African American population that does tend to have more issues with renal disease. So these calculations are pretty much mostly done by your computer systems now. However, if you do a registry exam, they're going to want you to kind of factor some of these things in they may give you the creatinine value from the serum and have you factor in the different components of the patient in order to do these calculations. So there are some examples in the book that you can take a look at those, just so you're kind of familiar with how to do these calculations, because it could potentially be on the registry as far as understanding how to perform these calculations, although most places the computer systems will do these for you now.